Hello everyone. Today we'll be covering an often overlooked benefit that power modules bring to the table: excellent EMI performance. If you're familiar with buck switching regulators, or you can remember your days as an undergraduate engineering student, you'll recall that there is an ideal version of the buck regulator, as shown here. The ideal regulator, with its high side and low side MOSFETs, inductor, and capacitors, is a great way to teach the basic functions of a buck regulator, but it certainly disguises some of the common real-world issues of this circuit topology. In reality, there are a few more components that show up in a buck regulator in the form of parasitic elements, which tend to cause trouble with the performance of your design. There are parasitic inductances in series with the high side and low side switches, as well as a high DIDT loop area on the input side of the regulator. Most problems with switching power supplies and noise are related to these parasitic components in the design. As you can probably tell, having excessive inductance in the high DIDT loop can create unwanted ringing on the switch node, and since the inductor is not an ideal inductor, this noise can make it all the way to the output voltage. With this background of the buck regulator in mind, how can a power module help improve EMI performance? Power modules can help reduce that high DIDT loop area referenced earlier by integrating some of the input capacitance close to the internal IC. Modules also reduce the high DVDT node area with an integrated inductor and smaller switch node. These advantages lead to improved EMI performance by mitigating EMI generated by the parasitic elements. This all sounds great in theory, but how does this translate to measured EMI performance in a real application? Let's first take a look at a 36-volt converter with an external inductor, the LMR23630. On this plot, you can see how the quality of the layout, and specifically the placement of the external components, affects the EMI performance substantially. As shown in the CAP-FAR example, you are no longer able to pass CISPR22 specifications with a poor layout and capacitance far from the IC. Now, let's take a look at the EMI plot with the LMZM33603 module, which uses identical silicon as the LMR23630 converter. We can see that even with a poor layout and external capacitance far from the IC, that the module is able to pass CISPR22 requirements. The module shows better EMI performance in both the optimal and poor layout scenarios. Keeping the external capacitors close to the IC is still recommended, but as we can see, the power module is much more forgiving in the scenario where close placement of capacitors is not possible. Ultimately, this means more design flexibility as the module-based design is much less sensitive to component placement. This is all a result of the smaller DIDT and DVDT loops that come with the integration of the inductor and some of the input capacitance. If you've learned one thing from this video, it should be that input cap position does indeed affect the output noise of your buck switching regulator, and that a power module can help improve your EMI issues. Learn more about the EMI benefits of power modules by downloading our application note, and visit ti.com/powermodules today to find your next power module. Thanks for watching.